Okay, everyone got their stuff turned in? Yes?
Now, but the last time when we were signing, pretty much my whole table besides Andrea didn't get to sign it, but we were all here.
Okay, I'll make sure. Sure. What's your last name? Who else didn't click in last time? Who else? What's your last name? Wolf. Last name? Who else last time didn't? Last time? Avion? Potter? You didn't click in last time? Okay, all right. All right. Well, this is our last meeting until, well, after spring break, right? We can come back and, so today we're supposed to be covering rational functions graphing, which is what we've already started, right? So we're going to continue that. And what I'm going to do is at the end, I'm going to give you, when I'm done talking, what I'll do is I'll give you a take-home. This is actually an exam review that I gave back in 2006. But what it has in it is sketching quadratic functions. Those are parabolas, a couple of long division problems, sketching a couple of polynomials, and then sketching a couple of rational functions. And that's kind of a summary of the main topics that will be on the next test. So it's something that you can look over spring break, and, you know, yeah, I'm sure that's what you'll want to do over spring break. Anyone else click in? No? All right. Well, let's pick up kind of where we left off. We ended class. I actually had to keep you a little late, didn't I? And we had graphed the 3x plus 5 over x squared minus 2x minus 24, right? So I'm going to move on now to the next one over here. X squared minus 4x over 2x squared minus 16x. And just remember that I'm going to be following the steps that I handed out to you last class, right, on a separate sheet. So that's what I'll be referring to when I say step A, B, C, D, E. This is what we're going to be looking at. All right, so the function that we have is the function f of x equals x squared minus 4 over 2x squared minus 16x. All right, what was step A of our process? Anybody not have the steps from last class that need them? No? What do? Check, right? Check to make sure that it's a rational function. So we do have a rational function here. So step B would be now to completely factor the numerator and denominator. So I'm going to rewrite the function factoring the top and the bottom. Well, the top, what can you do up here? Take an x out. So GCF, greatest common factor. I pull one x out. I'm left with an x minus 4. On the bottom, what can you do? Take a 2x out. And you'll be left with what? X minus 8? Okay, so that's your GCF out. Now, in part C, it says, look for common factors. If you have them, cancel them out, but remember that you will have a hole at the x value which makes those factors, that doesn't make sense, which makes that factor 0. If you had more than one, you say those factors. So do we have common factors here? X over x is 1, isn't it? Right? As long as x is not what? 0. If x is 0, you get 0 over 0, which is a problem, which is why we have a hole there. So what I'm going to do is on part C, I'm going to notice that x was a common factor. What that means to me is that if I take that common factor and set it to 0, which in this case turns out to just mean x is 0, right? That means that x equals 0, right here we're going to have a hole. Okay? We will have a hole in the graph at x equals 0. Now I showed you these last class. Let me see. What was it? X squared minus 4x. Oh, x squared minus 4x over 2x squared minus 16x. This was what our graph looked like. All right, this is what our graph at the end should look like this. And notice, it's hard to see it. Yeah, it's hard to see it, but right here, there's like a little orange dot there. The blue looks like it breaks apart there. That's my way of representing a hole. Now, we're going to do it a little different when we graph it by hand. We're going to really make sure everyone knows there's a hole there. All right, so that's what that step that we just did, part C, is going to give us. It's representing that hole. Any questions?
When x equals 0.
When x equals 0. So, yes. Uh-oh. Where's my... There. That's weird. So you're looking at the x value here, right? Here, x is 1, 2, 3, 4. We have a vertical asymptote over here. But at x equals 0, when we look at the graph and we try and look up or down to see the graph, there's going to be no graph. So there's a break in the graph.
X plus 2 and x plus 2 on top, then it would be when x equals
-2, exactly. Yes. So you have to set the factor equal to 0. Yes. Okay, D, find the x-intercepts. And how do we find the x-intercepts of a rational function? Just the top, the numerator. So we're going to set the numerator equal to 0, which means I need to set... That's the good question, right? Do we use the x or not? When we're doing this and we're setting the numerator equal to 0, what we want to imagine we've done is canceled those x's so that we're really just looking at this. X minus 4 over 2 times x minus 8. And here's the reason why we don't want to include the x. If we included this x, right, then we would actually say that we have an x-intercept at 0. But we just said we have a hole. So you can't have both. So when you're looking at the x-intercept and you're setting the numerator equal to 0, you're working off of this completely factored and fully reduced form of the rational function. Okay, so I'm only going to set x minus 4 equal to 0, which gives me a solution of x equals 4. And remember that this is a point, right? There's a point on the x-axis because it's an x-intercept. Any questions with that? Get this thing moved over here. Okay. What's the next thing? Part E is vertical asymptotes. How do you find the vertical asymptotes? You set the denominator equal to 0. But again, you go to this one, okay? You go to the one that's completely reduced out. So I'm going to set 2 times x minus 8 equal to 0. And this sometimes confuses students, all right? This 2 out front, they kind of don't know what to do with it. So they say, oh, I have a vertical asymptote at 2. But in fact, when you have just a number by itself, what you can imagine doing is just dividing both sides by 2, right? If I divide both sides by 2, I'll get x minus 8 equals what? 0. And so really that 2 plays no part in the vertical asymptote at all. Now, if it was 2x, now that would be different, because then you'd have to set 2x equal to 0. But since there's no x, we don't really consider it. And then solve for x here, you get x is 8. And what is this going to represent? Vertical asymptote. So this is going to be that vertical barrier, vertical dotted barrier. That vertical barrier, it forced our function up or down, remember? It forces our function to go up or down. Okay, next step. Part F, horizontal asymptotes. So what am I supposed to do for this? Degree of the numerator. So I'm just going to put numerator and denominator, and I want everyone to please understand degree, denominator. Okay. Tell me what the degree of each of these are. So go back and look at your function. What was the degree of, where the hell is it?
2.
Yeah, the degree of the numerator is 2, right? It's the power up there, the highest power. So it's 2. What is the degree of the denominator? It's also 2, right? Now, we didn't have this happen last class. What we had last class was the degree of the numerator was smaller than I always have trouble with that, than the denominator, all right? So I'm giving you a different scenario here because in our notes for horizontal asymptotes, remember that there are 3 cases. If the degree of the top is smaller than the bottom, if the degree of the top is bigger than the bottom, or if they're equal. And this is, I had that typo in there, right? Y'all fixed it? It was backwards. Y'all fixed it on your notes last class. So which of these cases do we have right now? Case 3, right? They're the same.
Why is it 2?
I think you're looking at the leading coefficient, not the degree. When you say a degree, this is a polynomial, right? The top there. Yeah. Polynomials have leading coefficients in degrees. The degree is the highest power. The leading coefficient is the number in front. No,
I know what.
Okay.
But I was looking at the.
Oh, but you're just ahead of me. That's all, I think. Oh. The answer is going to be 1. Yes. But let's look at why it's 1. So if the degrees are the same, what we're supposed to do is create a horizontal line that's going to be our magnet line. And it's going to have the equation y equals, okay, y equals, now the leading coefficient of the numerator divided by the leading coefficient of the denominator. So what is, not the degree, but the leading coefficient, oh, it's not going to be 1, I'm sorry. The leading coefficient of the numerator is what? 1, right? The number in front of the highest power. What is the leading coefficient of the denominator? 2. So you're going to take the number 1, and you're going to divide it by the number 2.
So you're asking for the
leading coefficient. Okay, so it's a little tricky because in case 3, the degrees match, right? That's what you start with. If the degrees match, then you have to go and look at the leading coefficients. That's what has to happen. Okay? If the degree of the top is smaller than the bottom, you don't have to look at leading coefficients. If the degree of the top is bigger than the bottom, you don't have to look at leading coefficients. The only time you ever look at leading coefficients is when the degrees are equal. Yes. Original. Yep. Good question. Okay, so because of that, since they're equal, I'm in case 3, which means y equals, I'm going to put LC num over LC dem, or den. Okay, leading coefficient numerator over leading coefficient of denominator. What's leading coefficient of numerator? We said 1 over leading coefficient of denominator. We said was 2. So y equals 1/2. Y equals 1/2. I drew it up here on the board last time. Remember that when you have an equation that represents a line, if you write y equals 1/2, what we mean is you draw a horizontal line where your y value is always 1/2. So if this is 1 up here, this is 1/2, right? That's 1/2. Then we're going to draw our magnet line, remember, only at the ends. It'll be like that. That's what part F got us, is how high up and down that little magnet line is. Go with me? Okay. All right, what's next? We're done with F. G, plot all the information we have so far. So we're ready to start getting a graph together. So here comes my graph. All right, let's start with the first piece of information we had, which was X Intercepts. Now, I realize we have the hole. We got the hole first, right? But that's going to be, we can only put the hole in when we start drawing the graph, okay? Because we don't know where the hole belongs. So, X Intercepts. We only had one of them or two of them? Where was it? At 4? So I go out 4, 1, 2, 3, 4. Here's 4. And I'm going to put, let's say, a big old blue dot there. That's my X-intercept. That's my only one. The next part that we found out was the vertical asymptotes, and we found one at 8, didn't we? So I'm going to go out to 8. So that's 4, 5, 6, 7, 8. And I'm going to draw what here? Vertical dotted line, right? This vertical dotted line is not part of my graph. It's to help me realize where my graph is going to go up or down forever. So there's my vertical dotted line. Cannot cross that. Next piece of information, horizontal asymptote at 1/2, right? Y equals 1/2. So if this is 1, this is 1/2 on the Y, I'm going to go out and draw what I did up here on this board. Just dotted lines out on the edges. And how far out do you need to go? Well, on this side, I don't really have a lot of graph over here, do I? So, you know, anywhere I want over here. On the right side, you need to get at least past the last thing that you know is happening. So I have a vertical. I need something to the right of that. So let me come out here. It's going to be right around in here. I wish I had kind of given myself a little more room, but is that okay? Is that all right with you? Okay, let's take, because I'm going to need a test point over here, and whatever that test point gives me, from that test point, I'm going to have to draw it out to the right, so I'm just trying to get it as far to the right as possible. Yeah. Any questions? Let's just take a quick poll to see if you're with me up to this point. What's next? We got the asymptotes up there, though. Test points. All right, so now what I'm going to do, I'm still in part G. I plotted all the information I had. Use this information to determine test points. They need to be between the x-intercepts and vertical asymptotes, and they need to have one on each end. So let's find some test points. How about in between x-intercepts and verticals? So I have an x-intercept here at 4. I have a vertical here at 8. I need something in between them. 5, 6? I'll go with 6. And what should I put here? So I don't confuse myself. I said put a little X there so that you don't think that this is part of your graph. That's just representing, I'm going to grab a test point right there. Right? If you put a dot, what might happen? You might think it's an x-intercept, right? Okay. So I've got one in between the x and the vertical. Then I need something on each end. So that means anything I can think of to the left of 4. 3, 2, 1, 1, 0, right? Anything I want. I'm going to go with 0. I like 0. I enjoy plugging 0 into things. So what exactly? What's going to happen if I try and plug in 0? I get undefined. right? So you know how I've said you can have any point to the left, any point to the right. We always have to be mindful of the whole, right? So we could try 0 and it's going to cause a problem, isn't it? So the reason why I wanted to make sure you saw that is because I don't want you to plug that one point you can't plug in and then realize later what in the hell is happening here. So if I try 0, it's not going to work. So what should I use? Anything other than 0. Well, I can't use 4 because 4 is an x-intercept. So we had said 3, 2, 1. I could use -1, anything. I'll go with 2. 2 is fine. So 2 I'm going to plug in 6. Am I done with test points? I need 1 on each end, right? I don't have anything over here yet. So 10. Now here's a rule of thumb you can use, and it's not in your notes, but if you want to remember it. How many x-intercepts do we have? Okay. How many vertical asymptotes do we have? 1. Okay. How many test points do we have? 3. You'll always have one more test point than you have x-intercepts and verticals combined. So if we have 1 x-intercept, 1 vertical, that's 2. We should have 3 test points. If we have 2 x-intercepts and 2 verticals, we should have 5 test points. 3 x-intercepts, 2 verticals, we should have 6 test points. It's just a rule of thumb, all right? So I know I have enough test points here. I can proceed. Now, how did we proceed with this? What do we do with these test points? Plug them into the original function, right? And I said you should try and plug them into the factored version of the function. So what was our factored? They won't matter because they're going to cancel each other out. So yeah, it would be fine for us to go into this one. What was the cancel one? It was x minus 4, x minus 8. Okay, so here I go to test. I'm going to do f of 2. I'm going to do f of 6. I'm going to do f of 10. And last class, we were right at the end of class. I know that I had kept you and you were all upset. But let's see if we remember how I was doing it like this short way. Right? Remember, I was only determining whether or not the answer was positive or negative. Right? So if I plug 2 into this, let's see what happens on the top. You get 2 minus 4 is a negative number. So I have a negative number. I divide that by, well, 2 is always going to be positive, right? So I don't have to worry about that. But then what's 2 minus 8? Negative 6, so that's a negative number. So a positive times a negative down here should give me a negative. And then what is a negative divided by a negative? Positive. So what that tells me is that when I am at at positive 2 for x, so when I'm at this test point, I should draw a point, I should put a point where? Above the x-axis. Where? In this class, I'm saying it's okay to put it anywhere above. I don't care how high it goes or how low it goes. Well, it could. That's the thing. It depends on the function. In this one, it doesn't, but it could. And that's the thing. We don't really know, okay? And we don't care to know. But I'm going to keep in mind that when I go to the left, I'm going to have to go back to this magnet, right? So it might not be good to put it way up here because then I'm going to have to come all the way back down, right? So I'm just going to throw it right around here. Does that seem okay to you? That's above the x-axis. I realize when I draw this, it's going to come this way, and it'll flatten out towards that. And I'll be happy with that. Questions? Now, I want to show you something that is a little bit dangerous. I've seen students do this, and this is the original problem, right? That's the original one right there, before we did any work. I've seen students try and do this on this. And let's talk about why you can't. All right? If I plug in 2 right here. Okay, so I'm trying the same thing. I'm plugging in 2. If I plug 2 in here, what do I get? 4, that's a positive number, right? Okay, so you say that's a positive number. And then you say, plug in 2 right here. What's 4 times 2? 8, it's a positive number, right? So you put a positive number here. What's the operation happening between these two? Subtraction. If I take a positive number and subtract a positive number, is it positive or negative? Could be either one, right? Think about this. If I do 5 minus 4, I'm taking a positive number 5 and subtracting a positive number 4. This turns out to be a positive number. But if I do 6 minus 7, 6 is positive and 7 is positive. If I subtract those, it's negative. The key to this part working is the fact that it's factored, which means we're multiplying things. Multiplying things, we always know what the answer is. I hope that that makes sense. So the only way you're going to get this to work out correctly for you is to actually do it the right way. So plug 2 in, what would we get? 4 minus 4 times 2 would give you 8. We did that. 2 squared was the 4. We're plugging in positive 2, right? Then here, 2 squared is 4 times 2 would give you 8. Minus, and then 16 times 2 is 32, so minus 32. The top is negative 4. The bottom is negative 24. So that's positive 1/6. Positive 1/6. So when we put this point up here, it's actually like really close to the x-axis. But I told you, I don't care. This shortcut to me is worth more than knowing the exact value. Questions? Okay, what dotted line? That's why I don't draw it all the way across, because I don't want that to even be part of what you're thinking right now. As far as like, do I put this point above or below this thing out here? Well, don't worry about it. This is what's happening at the end. Just forget about that. It could be that this dot stays below it, but there are other functions where it could actually have done this, gone up, and then come back down and dive down. So there's no like always going to be this way. Okay, let's test the other 2 points. I need to plug 6 in. So 6 goes up here, 6 minus 4, positive, over, let's see, 6 minus 8 is negative, times 2 is still negative, so I get negative here, positive over negative, it's negative. So that means when I go to 6 on my graph, I need to put a dot where? Under it somewhere. And again, I don't really care where. I just put it below the 6 a little bit. And then on the last piece, 10, plug 10 in, you should get a positive on top, and you should get a positive on the bottom, which means that positive divided by positive is positive. 6 got plugged in here. 6 minus 4 is 2. 2 is a positive number, so I'm saying the top is positive. 6 minus 8 is negative 2. 2 times negative 2 is a negative number. So the bottom is negative. But a positive divided by negative is negative. Yeah, this I was showing you. If you want to not do this and you want to get the exact value, you have to go through and grind out the exact number. You can't do this plus minus thing. Okay? All right, so that means at 10, I'm going to put a dot where? Above. And how far up is up to you, right? How far up is up to you. So watch, your thought might be, hey, look, I'm going to keep it below this because it looks like it's going to go like this, right? It's going to turn out to be above. All right? So that's why we don't want to, that's why we don't care. So you put it there or you put it here. I don't care, but you can't have 2. So where do y'all want it? Above? Okay, that's fine. All right, have we done all our test points? We plugged them in? Okay, part H. Put it all together with a continuous function. Don't forget the holes. Don't forget the holes. Where was our hole happening? At 0. Okay. So how did I tell you to graph this? Again, this was at the end of class. Where do you start? Connect the dots, right? Start with the first dot that you see as you would read this from left to right like a book. So go to the first point that you know exists on your graph, which is this one right here. Yes? And try and draw it out to the left. So if I draw this to the left, what has to happen? It goes towards this magnet, right? It cannot come down here, right, and then go to the magnet, because it would create X intercepts if I did that. So all I need to do is just draw this out and then kind of flatten out towards that dotted line, and I'll be done. I don't know if it's coming from the top or bottom. I do because of the computer picture, but in my picture I don't know. So I'm just going to go like this and just flatten out towards it like that. It's okay. You wouldn't get taken off at all for that. This all goes back to this idea. With polynomials, we had like left-hand behavior, right-hand behavior, and then we knew touch and cross, and we would say something like maybe it did this, but then another student could have drawn it like this, right? Or another student could have drawn it like, oh, and all those would be correct, yes? Same thing with this. A student may have picked that point a little above, a little below. We're all going to have similar characteristics in our graph. Okay, so now I draw to the right. From this point to the right, what has to happen? I'm going to have to go down and touch that one, right? Now I know I'm going to cross through because the next point that I have is down here. So I'm going to draw a little, connect the dots from here to here to here. And when I get to this one, I have to start continuing to come out this way, and you can kind of tell what's going to happen, but let's think through this. I'm trying to draw to the right without picking up my pencil. There's a vertical barrier. Vertical barriers force you up or down, and it's down here. And it's remember last class I said it's not because it looks like it's down. It's because if you turn back up, you create an X intercept right there. So it's going to continue down forever like that. So I put a little arrow on it. Yes? That's right. Y-axis is okay. We never found the y-intercepts, right? I didn't ask for them on this. Not the y's. No. Yes. Which one? Where? This, oh, above or below doesn't matter. No. No worries. That just tells you you're headed towards that value of one half. From the bottom or top, we're waving our hands at that and saying, look, in this class, we just don't know enough yet to be able to get that precise. Yes.
What I use for the test points is well, the same, but with numbers instead of
Yeah. Your graph would be even better than mine, but I'd be done before you. That's the only difference. Time, it saves time, unless you're using the calculator. Yeah. So you have to be careful with the calculator. Make sure your signs are correct. If it's a negative, you're testing. More test points would give you more information. Yes. Which is what the computer is doing when it's graphing it, right? Yeah, if there was another one here, but see, if we had another X intercept, let's say we would have had one here, we would have also had to have had another test point in there. So we would have had a corresponding test point up there. That makes sense? And so we would have known we would come down and have to go back up and back up. See, it would have led us to it. Okay, so I've run into a vertical. Now I have to pick my pencil up. I have to go to the other side and look for a point. And I have only one, right? So I have to draw it to the left and to the right. So to the left, vertical barrier, which way? Up. Can't come down because can't cross the x-axis. So it's got to go up. So I'm going to draw this up, and then when I draw it to the right, it's going to go towards the magnet, right? Okay. So to the left, it goes up. To the right, flattens out. Yeah, that's good. Flattens out towards that thing. And that's it. Hole. So what about this hole? That's right. We don't want to forget about the hole. It's the very last thing on your thing here. Don't forget the holes. We said we had a hole at x equals what? 0. In my graph, the way it looks right now, it appears that my graph just goes through and I have a y-intercept, right? I need to come in here and somehow show you that that's going to be a circle, like a hole. So I have a way of erasing on this computer, but every time I bring it up, this certain eraser, it like makes my computer crash. I don't know why. It's only while I'm videotaping. So what I'm going to do is I'm going to draw like that, okay? That I'm just drawing white on top. And now what I'm going to do is I'm going to put a hole. That hole's a little too big. Here's a hole. Man, why did it do that? There's a hole. Theta, yeah. And it goes through like that. There's my hole. So, what was it, 0? No. The hole was at 0, at x equals 0. Left and right, it's saying the hole appears when x is 0. That means left and right, x is 0. That's right on the y-axis. How high it is, we don't know. We just know that the function doesn't exist, right? It's like you're clipping it. Well, in Calculus 1, you actually figure out where the function's going to. It's headed towards somewhere. You can tell from this graph that the function does appear to be headed towards some value from the right side and the left side. We don't really know what this is in this class. So let me just bring back this picture. There we go. Our picture's pretty good, right? It's not bad. Now, it took, what, 30 minutes or something to do it, right?
That's how much time you're going to get.
Yeah, I mean, you can only have a few of these, right? I mean, you can only have, I've given the next exam I've given before has had like sketch 1 parabola, do 1 long division, sketch 1 polynomial, sketch 1 rational function. 4 problems. I've given tests like that, and you take the whole hour, 40 minutes, and you're in a hurry. So, okay, next one. Let's look at this because we haven't seen this case yet. Okay, we haven't seen that yet. I don't know. I feel like I should be saying you're welcome right now for bringing so much joy and happiness to your day by doing this. But I don't need to hear thank yous. So
Thank you.
this is very this is fun, huh?
Okay, you made me laugh.
All right. Okay, what's the first step? Make sure it's a rational function. So it is. Y'all realize I'm kidding, right? Okay. All right. All right. What's the next step? Factor it out? Yep, factor it out. So what can you do up top? Factor out an x? Do you want me to do negative x or x? Negative x? Yeah, negative x is going to help you see that it's going to turn into a difference of squares up top. If you don't factor the negative out, it might be harder to see that. And that would throw everything off, right? What I'm saying is if you just pulled an x out, you'd be left with that. And you might fail to realize that that's the same as 9 minus x squared. And then you could still break that down, 3 plus x, 3 minus x. Okay, but we were able to, I'm going to do more factoring over here in a second. How about the bottom? So -6, +5. Okay. And let me go that additional step on top. I've taken the -x out, but now I add difference of squares. On the bottom, x -6, x +5. Now in this step B, or step C is where we look at the factors. In step C, we look to see if we have any common factors, anything that cancels out. Anything? No. So that means we have no holes. Part D, X intercepts. I'm going to set the top equal to 0. The fact that I already have it factored is going to make that easy. Easier. 0, -3, and 3. So I set this equal to 0. I get x is 0 from the first one, -3 from the second one, +3 from the third one. I have 3 X intercepts, don't I? Only the numerator. After you've canceled the factors, though. Yes. Now, this is not good news, because that means at minimum I have 4 test points at this point in the problem, right? Remember we have test points we have to plug in? I have 4 at least right now. Part E is going to make us even more upset. Okay, so E is to find the verticals. To do that, you set the bottom to 0. So I'm going to have how many verticals? 2. I have vertical at 6 and -5. 2 verticals. Now, notice I'm not writing anymore what these are, because I'm assuming that you're kind of catching on to it. You'll have this sheet with you during the test, so you'll know it even says in here what they are when you find them. All right, part F. What's the degree of the numerator? So degree of the numerator is 3. Degree of the denominator is 2. What case are we in then? Case 2. We haven't had case 2, have we? We have the numerator is bigger than the denominator. Any question on where I got the degree from? This 3 coming from the fact that the highest power up here is 3. And the 2 coming from the highest power here is 2. So in case 2, if the degree of the top numerator is bigger than denominator, then you won't have any horizontal asymptotes. But look what it says here on your further down. Dotted line acts like a magnet pulls. If you don't have them, then what? The function will act like a polynomial at the ends, meaning polynomials went and did this left, right, up, down thing. That's what it will do at the ends. Okay? Now, whether or not it's up or down, we're going to have to figure that out, and we'll use the test point to figure that out. Okay. We are going to say here no horizontal asymptote. I think it's graph time, right? G, step G. First piece of information I'm going to put here, my x-intercepts, we're at what? 3, -3, and 0. So 0, 3, 3, -3. I'll do it in blue again. So -3, 0. That okay with my x-intercepts? How about verticals? Where are my verticals? 6 and -5? 4, 5, 6, and -5. And I'm going to draw vertical dotted lines here. Horizontal asymptote. There's none, so I don't draw anything. So that's all the information I have. That's everything. How many test points should we have? So we had 3 X intercepts, 2 verticals. We should have 6 X intercepts. 6 test points. So I said they have to be between all the verticals and X intercepts. So look at this vertical here. Look at this X intercept. Something in there. -4. Something between these 2 X intercepts. -1. Something between these 2 X intercepts. 1. Something between this X intercept and this vertical. 4. Okay. Am I done? No, I only have 4. I need 6 of them. So which ones am I missing? The ones on the ends. So how about 7 over here? And how about over here like -6? So now you have the pleasure of plugging 6 different values into the function. And this is where you want to try it on your calculator and see if you already did it. It's going to see who was faster. But so what are we going to plug these into? The factored version, right? -x, x plus 3, x minus 3 over the bottom, which was x minus 6, x plus 5. So I'm going to plug in f of -6, f of -4, f of -1, and then over here I'll do f of 1, then f of 4, and f of 7. Just make sure you're plugging your test points in. Don't accidentally plug in one of your x-intercepts or something, or your verticals. It's going to cause all sorts of confusion. All right, let's see what happens here. Be careful. I'm plugging -6 in right here. What's -6? Positive, so I have a positive. Then -6 right here. Negative. Then -6 take away 3 is -9, so it's still negative. All over. -6 minus 6, negative still. And then -6 plus 5 is -1. Okay. What's the numerator? Positive, because these two together are positive, right? Positive times positive is positive. And the denominator, these two together, positive. So positive over positive is positive. So I should have positive. And then do the same thing for -4. You should get a positive, then a negative, then a positive, and then you should get a negative and a positive. The top is negative, the bottom is negative, right? Is that right? No, something's off there. Let me see. Negative. Yeah, this one's negative, sorry. So the top is positive, the bottom is negative, which means you have a negative number. Let's just do a quick poll to make sure you understand what I'm doing here. Yes? I have to, according to the steps, I have to pick a number that is on the left end, and I have to pick a number on the right end. It's just one of your test points always. You always have to have them in between the x-intercepts and verticals, but then you also need one on each end. Because we want to know what's happening on the end, right? We need the end behavior, and that test point helps us determine what's happening. Okay, what about -1? If you plug -1 in, you get positive, positive, negative, then negative, and then positive, which should give you negative over negative. That should be positive. Take it easy. When you plug in one, so y'all voted, most of you said yes, you're okay with that. So I'm just going to go through the next and just say what they are. Someone who got them, tell me what they are. F of 1, it should be negative, positive, and negative, yes. So these are switching. If you notice, we started out, it went as positive, then negative, then positive, then negative, then positive, then negative. But I told you last class, it won't always do that. So you need to be careful to just test each one. All right, I think we're ready to put these test points on here, right? Everyone got that? Okay, -6, I'm going to put a point where? Above. Then at -4, below. At -1 above. At +1 below. At +4 above. And at 7 below. There it is. Looks crazy, doesn't it? I put them the same height, like these are about the same height, these are about the same, below. You don't have to, all right? Again, how high and low you put those doesn't matter. So we're ready to draw. Let's start with this leftmost point. Like I said, you always start with the leftmost point, and you have to draw it out to the left and to the right. The part to the right, I think, is the easier of the two. What do I do if I try and draw this out to the right? It's got to go up, right? Can't go down because I don't have an x-intercept there. So the right side's going up. What about the left side? There's no magnet, right? There's no magnet pulling it. Oh, be careful. No. Hold on. You don't look at, what I meant by it acts like a polynomial is that the ends of polynomials do this, right? Both sides up, both sides down. But the idea is that it goes up forever or down forever. That's the idea. We don't look at the degree and use that table. Okay? It's just that we know that at the end it's going to go up forever or down forever. That's all we know. So is it going to go and turn and go up forever, or is it going to go and come down forever? Which one? Can't go straight out, or we would have had a horizontal asymptote. Right? If it comes out straight, that means it flattens to something. They don't behave that way. What's that? Nope. Nope, we can tell just by this. It's got to go up. Why? If it comes down, it's going to cross through the x-axis. Right? And we'll create an x-intercept that we're not allowed to have. It can't flatten out because it doesn't have a horizontal. We would have found it.
So you were saying that the x3 doesn't mean
No.
you can't do that?
No. It's just, when I say it acts like a polynomial, polynomials, on the ends of polynomials, you have two scenarios, up or down, right? That's it, up or down. For us, we know it's going to go up or down. It's just a matter of which one. The test point itself tells us. How do you mean?
I mean, that's the way.
That's the way it's supposed to go.
But doesn't necessarily mean that it was going to go up that way because we could have gotten an x-intercept?
If we would have had an x-intercept, then yes, it would have come down, but then we would have had another test point on the other side, and we would have had a lot more information of the graph.
Okay.
But this is not possible.
Because we're not determining, can't determine when.
X-intercept would occur there. Not going to happen.
What I mean is like determining the endpoint is different. You can't just draw. You know that's going to go like that.
Mm-hmm.
I mean,
No.
in this case it is, but.
Yeah, in this case it's going, well, I don't know what you're...
Because x3 goes like that.
Okay, yes, throw that out. Throw that out completely. We're not looking at that at all. Okay?
Because
It's not a polynomial.
polynomials are rational functions.
That's right. It's a completely different class. It just, we know that if they don't have horizontals, then the left and right behavior is either up or down. Maybe I should have just scratched the polynomial out of that note and said it doesn't act like a polynomial. I should have just said it either goes up or down. That might have made it easier made more sense that way. Okay, so I have to now pick up my pencil and go to the next point that I have, which would be this one. And now I need to draw to the left and to the right. So to the left, I'm going to run into that vertical barrier. I'm going to be forced to go which way? Down. So I'm going to go down. So I'm thinking through this. I'm going to go down like this. And then, like, this is seriously connecting the dots for quite some time, isn't it? I'm going to come up to this dot. From here, how do I know whether or not I bounced or touched off of that? Well, the fact that I have to come up here, right? Which means I cross through, and then I get up to this, and then I have to come back through, and I cross through, and I come down, then I come up through here, and I cross through, and then we'll see what happens there. So I'm going to try and draw this Remember, rational functions are nice and smooth and continuous, so I don't want any weird corners on these. Try and curve this thing out. Not great, but okay, now what? It's got to go up forever. Because this vertical is in my way, I can't turn back down. So it's got to go up forever. And now I have to pick up my pencil and go to the other side, go to this dot here, draw to the left, down, to the right, down. For the same reason this one had to go up.
How do I know if the functions are down or up? Like,
Right here?
no, the other one.
Which one? This? This one right here. I don't know. Okay, so when I'm drawing this way, I have that vertical barrier in my way. If I try and come up, right, I will have to cross through the x-axis. So, and there's not an x-intercept there. There's one here. And remember, you can't do something crazy like this. You can't turn and go back, right? Why can't you do this? It's not a function. It would fail the vertical line test. So you can never turn back on yourself like that. We good? All right, so let's take a look at the graph of this with the computer and compare it. It was, I forgot, negative x cubed plus 9x squared, right? And on the bottom was x squared minus x minus 20? 30. No, something ain't right there. What was our original one? Plus 9. Okay, okay. Oh, no, that's right. Oh, 9x. I put 9x squared. I created another x-intercept. There we go. Now let me zoom this out a little bit. There we go. Okay, now it's hard to see it in here, but let's talk about that left end. Ours went up and it turned and it went back up, right? Now there's actually this weird dotted line in here, okay? That weird dotted line that our graph actually follows. This is called an oblique or a slant asymptote. I'm not going to test you on those, but I want to show you where they come from, okay? Because there's even more detail you can get in these if you're willing to go another step. I want to show you it because anyone going on to do more and more math should know how these come about, all right? So we've got this, our graph does do something like this. This is going up forever. Ours turned up real sharp, right? But hey, pretty good. Went down here on the left. It went up. It's hard to tell that we do this thing, like we really exaggerated that, right? But let's see if we zoom in on this a little bit. You can kind of see I zoomed in, and now you can kind of see that up, down happening there. See it? And let me zoom back out. You can see this right side. We dipped down, then this turned, and that's following that red line. It's going to go down, keep going down forever. So I think we got all the characteristics that go with that picture. Do you agree? Okay. So let's talk about this slant asymptote. Does everyone see that this dotted line right here is a line, like y equals mx plus b? Right? It should be a line like, there should be an equation for it. Okay, this line is somehow telling you what happens when x gets really big, right? It's what's happening at the ends. Okay, now just bear with me for a second, all right? Again, I'm not going to test you on this, but this doesn't mean turn me off completely for, this is like good bonus material, bonus problem on a test, all right? Negative x, the original function was this. And then x squared minus x minus 30. And the question becomes, what happens when x gets really, really big? Okay? So let's just consider this for a second. if this number gets really, really big, look at this almost like a polynomial just by itself. What would be the right-hand behavior of that up there? If it's a polynomial, forget the denominator. That's a third-degree polynomial, has a negative leading coefficient, so it would go what? Down? It would go down on the right? Okay. And what would it do on the left? It would go up. So I'm just going to draw that. It would go up on the left. It would go down on the right. That's what the top would do. In the middle, we wouldn't know if it was just a polynomial. What about the denominator? It would go up and up, wouldn't it? Okay. So this is a little confusing, but let's try and figure this out. Let's look at the right side first. This right side. The top says it would go down, but the bottom says it would go up, so they're like conflicting ideas, right? But which of these is bigger? Is x cubed bigger or is x squared bigger? As you put bigger and bigger numbers in. Cubing something is going to be bigger than squaring it, isn't it? So this one should dominate the other one. In other words, this top one should dominate the bottom one. So the negative is the effect. Okay? Same thing on this side, but see, these both want to go up. So if they both want to go up, then, you know, hey, it's going to go up. All right? Does that make sense? All right, but that's not the technical way we do it. All right? Here's how we do it. Long division. So we take this original expression, negative x cubed plus 9x squared, and on the outside we do the division here. Remember that? Oh, and I'm also going to put 0x plus 0 in my division box because I don't have an x term, right? Yes, this is for the slant or oblique asymptote. What? It won't be tested, but it'll be probably given as a bonus. It's in the homework? Yeah, but I've told you don't do the homework for this section, right? I'm going to send you home. You do not have to do the homework for 5.3. You're going to do this instead. Okay? All right, so what we do first is we ask ourselves, what do we multiply x squared by to get negative x cubed? Negative x. Okay, so then we multiply the negative x here. We get negative x cubed. Multiply negative x times negative x here, and that gives us plus x squared. And then we multiply negative x times negative 30, and we get plus 30x. Then we come through and subtract this, right? So change the signs and add down. So what do you get? 8x squared, negative 30x. You know with me? Now we say, what do we do to what do we multiply x squared by to get this? 8. Yes? What do I multiply x squared by to get 8x squared? So plus 8. And then come through 8x squared. Then what? Minus 8x. And then finally 8 times negative 240. Then I come through and I change the signs. Negative, plus, plus. We add down and get negative 22x plus 240. That's the remainder, right? We stop there. So what we would do is we would say up here, plus the remainder, negative 22x plus 240 over x squared minus x minus 30. And now for a very interesting but very important concept that you will be dealing with in calculus, all right? I would like for you to consider for a second the fact that our remainder, what is the degree of our remainder? What is the degree of it? 1. What's the numerator of the remainder? What's the degree of the denominator of the remainder? 2. So this really kind of looks like it's like an x over an x squared, right? Basically, x over x squared. And what is x over x squared? Really kind of, it's like 1 over x, isn't it? Tell me now, please, what would happen if you take this expression, 1 over x, and you let x get huge, what would happen? It would approach what? It would approach 0. Do y'all understand that? If I take 1 divided by x, and I let x get big, that fraction gets small. 1 divided by 2, then 1 divided by 10, 1 divided by 100, that gets small. So what I'm trying to get you to see is this. This right here is the same as this expression. It's the same thing. Long division created this new thing out here. But as x gets big, which means as we go out on the ends, this thing right here, this whole thing gets smaller and smaller and smaller and smaller and smaller and smaller. This piece that's left right here, see this? What is that? Negative x plus 8. What is that? It's a line. And guess what line it is? The slant asymptote. See, because what's happening is that you go out further and further, this right here basically vanishes away to nothing. And this right here just continues to be what it is. It is a line. I hope that makes sense. So if I go here, it's hard to see it. Let me see if I can zoom in again. Why do we have -1? Negative x plus 9x. Yes, but it should be negative x minus 1, according to that. Did we get this right? Yes, negative x cubed, positive x squared. Oh, you know why? I put the wrong freaking thing in here again. Look, I put squared in there again. Okay, so, all right, so I'll fix it. Watch. I'm going to go in here to this. Look, squared. I know. Okay. There's still slant asymptote. This is now, what we just found the slant asymptote for just now is this function, which looks different than the one we just had. And notice that here's the slant, right? Notice when I zoom in, look at this line. What's the y-intercept? 8, and what's the slope? It's -1. So it's negative x plus 8. That slant asymptote is negative x plus 8. Okay, so I made the mistake of putting the squared in there again. I shouldn't have. Oh well. I hope you get the idea, because that would be the bonus. The remainder goes to 0. That's right. The remainder vanishes. Yes, to 0. So what's left, the only thing of importance for us then are these pieces that are in here. Make sense? It's the original function rewritten this way. Is the blue. Yes. But if that happened, then basically this piece right here would wind up being what the exact graph looks like. I mean, the original graph would look like that. That's right. It creates this blue part, determines the dotted line that would be the magnet of the ends. But see, we said our ends went up forever or down forever, right? That's what we said. If we had done it correctly, they do, but they follow a pattern. They follow some line that would come through here, and then we could have said, oh, it goes and it follows that dotted line, instead of just saying, hey, it goes up forever. We didn't do that, and I'm not going to ask you to.
When you look at the remainder, is the remainder ever going to really?
It'll always go to 0. I don't know if that's what you're going to ask, but.
Yeah, it should, because the remainder is always going to be, the denominator is always going to be
bigger. Exactly. Which is why we use the long division, because that remainder part will always go away. The other pieces will be what is left. So it's interesting. That's extra credit. Yes. Okay. I think we're good. Yeah? Y'all good? Or do y'all want to see the last one with the hole? It's extra credit. Well, let's do this. On the test that you have, whenever that is after spring break, I will offer a bonus at the end that says, find the slant asymptotes for the rational functions that you just graphed. You don't have to go graph it again, just tell me what it is. So the answer would have been here, well, yeah, whatever, negative x plus 8. I screwed it up, but yes. It's just one, all this is long division, yes. Okay, all right, so what I'm going to do is I'm going to cut you out of here early unless y'all you're opposed to that. I'm going to let you go early. I have old stuff here to hand back to you. I had all your quizzes from last time, and I forgot. I had them graded and ready to go. I forgot to put them out here, so what I'm going to do is I'm going to put your quizzes out here. Is Juan here? Lobato? Juan Lobato? Let me see. Oh, he is? Okay. Now, look, please, I know you want to get out of here, and I know it's, it's early. I'm letting you out quite a bit early, right? Please come through and pick up your stuff because, I'll wind up just having this huge pile. Then I'll put the take-home assignment, which is going to be due the Tuesday that we return. So this is equivalent to homework, all right? But I would like to collect it as a quiz grade, all right? So this right here will be sitting on this table. Take one of those. Turn in your clickers. You also did a long division problem in class as a quiz. If there's a check mark on it or nothing on it, it's 100 unless there's a numerical grade. So 2 quiz things to pick up. What is that? Oh, we turn in the very beginning of class, right here. You next time turn in the beginning, okay? Or I won't take it. Or I won't take it. All right.